Good morning, all. This talk I'll brief about the extra-galactic planetary nebulae studies. So this is going to help in the mutual way that how we have understood the science of planetary nebulae and the evolution of the intermediate mass stars in one way by looking at them in a different galactic environment. And another way that how this planetary nebulae are very helpful in tracing the galactic environment, which are very crucial to understand their formation and evolution up to say at the distance of more than 30 megaparsec. So briefly, I will mention that and how this newly, this upcoming facility, like particularly the MSc with the IFU facility, or even the larger telescope, how they are going to improve this study. And this study is somebody at the infant stage right now. And just to give you a brief outline, I will be speaking very brief introduction about planetary nebulae and what are their importance, why they are very important in these extra-galactic studies. And the current status, mostly it is on the Magellan Cloud planetary nebulae and M31, and a few more new nearby galaxies. And then I'll discuss briefly about this very, something which is very surprise to us actually, why this luminosity function is invariant, and also just tell you actually how we can use these new facilities to explore more on these objects. So not to say more on here because we know that planetary nebulae are formed after the AGB phase. At the tip of the AGB phase, the star loses a lot of its mass, the low and intermediate mass star, and that ejected mass expands and disperses into the interstellar medium with some time scale. And meanwhile, the core of the AGB stars, they shrink and become hotter and hotter. They are hotter, but their radius is smaller, but they evolve in the constant luminosity track like this. And this is the region that you find them when these two time scales overlap. The hot UV radiation from the central stars, they ionize the nebulae around the stars, and then these nebulae are very visible by their own emission lines, spectral lines like oxygen 3 lines, nitrogen 2 lines, etc. And this has been quite, and later the dispersed to the interstellar medium, star fades to the white dwarf stage. So this is the slide that I'm going to discuss in more detail than later on these points. Is that actually basically this mass, these objects, they trace the evolution of the low and intermediate mass stars, that is 0.828 solar mass. Again, this limit that depends on the metallicity and this initial mass. Okay, so the evolutionary track depends on that. These two are the very important parameter for that. I can refer to this paper. And also the mass returned to the interstellar medium and the chemical enrichment of the galaxy. The planetary are doing very important role, especially helium, nitrogen, carbon, and sulfur, and S-class elements, and also different types of molecules and grains. These are being synthesized in the atmospheres of the AGB stars, and they are thrown out to the interstellar medium, enriching the galaxy. And again, the grains, the type of grains, the amount of grains, everything formed, and the mass loss rate, everything depends on the metallicity. Is that okay? So, moreover, the oxygen is a very abundant element, which is present, well measured in planetary nebulae. Several planetary nebulae we have measured it more accurately. And this is a metallicity indicator because oxygen is least changed in the evolution of the low and the intermediate mass stars. Only at the hot bottom burnings, it is being touched. Otherwise, the oxygen abundance of the shell, planetary nebula shell, they reflect the progenitor throughout the abundance. So they are very important tools to probe the metallicity of the progenitors. Okay, and again the stellar population studies, the central star mass distribution and the initial mass function, and these are being derived by looking at the nebulae around it and deriving in their mass at the core. Okay, and again this again depends on the metallicity, because higher central star planetary are expected at low metallicity. I'll explain why later. And we have another crucial question here to address, whether this star will end as a kind of a hydrogen-rich central star or a hydrogen-poor central star. How it happens, where it evolutionary track deviates from the hydrogen-rich central star. These are not known questions so far. I mean, these questions, the answers are not known. So we have been studying only those planetary nebulae so far in the disk and if you really observe the planetary nebulae even in the galactic bulge or extra-galactic region, then what we see there is something which is which cannot be really explained by the present understanding. So that means that is very sensitive function of the metallicity. And even the multi-wavelength astronomy play a crucial role here because X-ray it traces the hot bubble which is being pinch of bubble and which pushes the nebula out. And UV and optical region emissions too, they are very important to trace the elemental abundances and the other diagnostics of the planetary nebulae. And IR observations are very important to trace the dust chemistry, dust and then mass loss, etc. So with these new facilities coming in this wavebands, there will be a lot of questions which will be answered. Hopefully so. Okay. And planetary nebulae are its spectrum is very unique. It can never be missed out. If you are really taking a spectrum, if you are medium resolution spectrum, or even 2000 resolution, say for example, and you will have great lines at 5007 Einstein. That is O3 line. We call this. These are the lines which are used to look at the objects even in extra-galactic region. So these objects, planetary, for example, they have something like 8,000, 10,000 to 12,000 solar luminosity. They will have that, and in fact, 12% of that luminosity is emitted in this line with a very kind of width of something like 1.5 angstrom. So much power is being emitted at this line. So they are very crucial to study this, and it also sees several emission features in the central stars of planetary nebulae, and this has been, many of them have been observed. More than 105 planetary nebulae have been observed to have Wolf-Rayet type central stars in our galaxy, and a couple of them have been discovered in the extra-solar, extra-galactic regime. And you can see this paper for the recent study of discovery of few of the Wolf-Rayet stars in Andromeda galaxy. So I'll just briefly say why these Wolf-Rayet stars are very important in understanding the stellar evolution model. And they are called population 2 because we also have population 1 Wolf-Rayet stars. They are for the massive stars. They are massive stars. But just taking the spectroscopy, one can never distinguish whether it is a population 1 Wolf-Rayet star or a population 2 Wolf-Rayet stars unless you know the luminosity of the star. So the luminosity of the star is much lower for the case of planetary nebulae, whereas for the population 1 Wolf-Rayet stars, they are much larger, to order of 2 more than what is for the planetary nebulae. And they are all seen at O4, O5, O3, C2, C3, C4 lines. They are high ionization lines, and they are appearing from the winds of the central stars. And they can be classified into different groups, whether it is an early type, medium type, or late type planetary Wolf-Rayet stars, by using this emission line strength in this lines. And if you look at the surface abundances of the planetary nebulae central stars, they reflect the interstellar abundance, of helium-rich, carbon-strong, and the oxygen is around 50. So this is interstellar abundance. So the classification of planetary nebulae central stars as Wolf-Rayet can be seen at this paper, although there are some differences in that. For example, you don't really see many of the nitrogen sequence in population 2 Wolf-Rayet stars, but whereas in the population 1, you do see the nitrogen sequence also. So, so these are the brief things that I would like to say on the Wolf-Rayet star of planetary nebulae. And the crucial question is actually the number is not small. Okay, around 25% of the central stars of planetary nebulae are hydrogen poor. They can either be Wolf-Rayet stars or the weak emission line stars. Probably they are connected, and PG1159 stars. Okay, so put together there are 25%. And showing that large mass loss rate and the broad and strong emission line features. So the question is, how do they fit into the current understanding of the stellar evolution model? And how do they behave at different metallicity? And what new physics that it's going to offer? This is one of the important questions that we need to address. And coming to that role of planetary nebulae in the extragalactic studies, the chemical composition of the parent stars can be easily traced by the limbs with that emission line spectra of planetary nebulae. And the limbs constitute a large component of so stars in the galaxy. More than 95% of the stars in the galaxy is low and intermediate mass stars, and they enrich these elements. And the metallicity variation among the within the galaxy is an important tool to understand the galactic formation and evolution. And this, since I said I said earlier, oxygen is a good indicator or good tracer of metallicity of these stars. So the radial and azimuthal function of the metallicity distribution among the galaxy within the galaxy will be very crucial to understand the galactic formation. And very importantly, the accurate distance to the galaxies can be measured using this planetary emission line at 5007, more than say 50 megaparsecs. So far, 30 megaparsecs people have measured, but with facilities like MSC or TMT, we can go even further. And molecules and dust at different galactic environment, this itself is a huge topic actually, and how it behaves at the low metallicity region, how the mass loss is happening in the carbon stars, and how they are different from the oxygen-rich stars, whether dust-driven mass loss or because of the radiation-driven, kind of photospheric-driven mass loss. These are the open questions which has not been understood. Although we have some good understanding about the silicate, dust oxygen-rich stars, how the mass loss is happening, which is given by the dust. And again, the stellar kinematics, dynamics, and parent star population can be easily traced with the planetary population. And this can also be, for example, this metallicity distribution function or this stellar kinematics, everything can be also studied using the observing the stars, using absorption spectroscopy. But the difference is, if you do that for a using observation spectroscopy, even to observe the stars in M31, you need to have 8 to 10 meter class telescope. But if you are switching over to planetary nebulae with IFU, then even 2 to 4 meter class telescope can be used to map them in the galaxy. So that's a difference. Again, the tidal cycle and the disruption of galaxies, tidal streams, which are observed in several galaxies, in the Andromeda galaxy and other galaxies also, they are important to understand how they are interacting, how mass is transferred from one region, galaxy to another region, galaxy, and galactic merging, or such a topic can be addressed using this. And intra-cluster PNE is one of the good example. They are a good example that these galaxies are interacting very strongly, and the mass is being transferred from one place to another place. And this planet will be observed within these galaxies. There are something like 300 of them have been observed. And again, this probe of dark matter halos of galaxies, that's also an important topic, because the kinematics of the matter there can be easily traced using the planetary emission lines. And with that, we can go with the larger distance, from the center of the galaxy. So they are very important in this. So more than 8,000 extragalactic planetary are known as of now, and 300 intra-cluster planetary are known. In our galaxy, we have something like 3,700 planetary. So how you can identify them? It's very easy that you image them in a narrow band at 5007 angstrom line, and then shift that wavelength and then take another image. At them, all the prominent spots here are basically mostly planetary. Okay, and if suppose you have some confusions, whether it is a planetary or those objects which can be confused with the planetary, like H2 region, compact H2 regions, or supernova remnants, you can apply these techniques. For example, planetary or point sources at extra-galactic distance, because 1 axion is equal to 5 parsec at 1 megaparsec distance. But a planetary even the evolved planetary is less than say 0.5 parsec. And they are very bright in O3 and their H alpha, but the H2 regions are the other way. Okay. So this O3 by H alpha plus N2, this ratio gives a very important clue on whether this is a planetary nebulae or a H2 regions. If you have confusion with confusing the supernova remnants, then The sulfur line can be used to see whether they can be, they are supernova or planetary nebulae, because H-alpha sulfur line ratio is very, very strong for, it is larger than 3.3 for the supernova remnants, whereas planetary it's the other way. And the thing is actually planetary they have moderate expansion velocity, unlike the supernova remnants. It has some 30 kilometers per second or something, whereas few thousand kilometers or 1,000 kilometers per second will be observed in the supernova remnants. And to come to this, actually, being the closest galaxy, and also the distance is well measured and it's very bright. So these are the points which has made us to understand the planetary nebulae in these two clouds, large Magellanic Cloud and small Magellanic Clouds, better than any other galaxy. And that's how we also understand the evolution of these objects at the moderately low metallicity from say 0.2 to 1 solar metallicity. And we know the distance quite accurately, so the central stars can be accurately placed in the Hydra diagram. And again, the advantage with the advantage of HST is that actually at this distance you can well resolve this planetary nebula. So in the extra-galactic planetary study, actually for distant galaxy, you can never resolve this planetary nebula because they are point sources at that distance. Whereas for LMC and SMC, you can resolve them, and after that has helped us to give a far better understanding of extra-galactic planetary are these two clouds than any other galaxies. So PLE abundance is also well studied in the Magellanic Cloud after the Milky Way. So these are the images of HST, and you see that what they are the morphologies of the planetary nebulae. They can be either spherical or kind of elliptical or bipolar. So these are the two major kind of bipolar and point symmetric, they are subclasses. Okay, because many of the objects which are showing bipolar geometry also show that point symmetric thing. So what means widely we can classify into round, elliptical, and bipolar. And again, this is connected to the initial mass of the star. For example, round you are expected from the low mass star, elliptical medium mass star, and bipolar high mass star. If the star evolves in a single entity, but that's not all, because the interaction with the interstellar medium again changes the morphology. However, that morphology of this planetary nebulae in the early stage, they give you a lot of clue about their mass and their evolution. And some of the key findings here is actually the bipolar planetary nebulae SMC is quite low compared to the number seen in LMC. So that shows actually there are low mass stars. Okay, and the carbon is depicted in bipolar planetary and the N is enriched. This is an indication that the star has evolved in a single entity. That means the direct influence of a binary system is not effective there. It may be there, but it's not effective. Okay, like making this common envelope and then stopping this nuclear evolution further and then eject the matter out. So these are communications are happening. We have to understand that binary interaction in the stellar evolution is another topic to be studied. And so far we know that C to O-rich AGB stars they are higher at low metallicity. For example, SMC has only SMC has 11, whereas LMC has 4.5, Milky Way has only 1. So this is understood because of the low metallicity, what you say, when the star evolves, all of them have that significant oxygen abundance as the star evolves. When carbon is made, newly synthesized in this third reduction process, C and O coupled together because they are the molecules which have high affinity, and the remaining oxygen or the remaining carbon will form that their respective grades. And at the low metallicity, you do see this pattern because for silicates to form, you need a metallic core. So when at low metallicity, the metallic core doesn't form very efficiently. That's how actually the mass loss rate and the dust production rate are low at low metallicity. And if you see here that the N by H ratio, the N by H ratio with the metallicity, you can see a clear trend. It increases with the metallicity. And these are elliptical PN and these are bipolar PN. So bipolar PN, always the nitrogen is enhanced for much larger than the elliptical PN. And this average central star mass is having studied for a handful of Planetary Nebulae in SMC as well as in LMC, and they are plotted here. Okay, and the mean mass is 0.65, whereas the LMC SMC shows that higher central star mass, larger central star mass. This can be easily understood because at higher power mass, the models also predict actually at lower that higher power mass will be formed. This is very simple because the mass loss is not very efficient. So mass, the envelope is thrown out at for a longer duration, and meanwhile the shell burning continues and it adds more and more mass to the central star. That's how the central star mass is larger at the lower metallicity. And metallicity distribution function is a very important parameter for the people who are modeling the chemical evolution of galaxies. This is the LMC metallicity distribution model, and this is the SMC one, which are obtained from the photometric observation of the RGB stars. Okay, and these are for other galaxies, nearby galaxies, and these functions are all of them are obtained by the photometric observation, but photometric estimation of the metallicity distribution function has uncertainties. Whereas if you do the same thing with the Planetary Nebulae by the emission lens, the uncertainty can be reduced for greatly. And next to that Magellan cloud is that, of course, Andromeda, which has attracted the thing because it's nearby bigger galaxy, and it is at the distance of 785 kiloparsec when measured distance, and there are many planetary nebulae they are observed, and they were using this to trace the large scale structures of the galaxy, and important of them are actually northern spore and the southern giant stellar stream, and also the outer galactic region. So they studied the abundances of these objects, and then they made some important conclusions. They are here. N/O ratio and the helium by hydrogen ratio with the halo string planetary ratio, they are type 2:1. That means type 2 means low mass stars. Okay, that means less than 3 solar mass. Again, the abundances derived here are based on the empirical method, and it has its own uncertainties. Okay, if you want to really derive the abundances more accurately, you have to really make a kind of thermal photonization models of this planetary nebulae, and then you have to derive that. This empirical way of deriving this has several reasons to make this uncertain values. Okay, several factors are included with that, but still this is a very useful thing because you are applying the same method to every planetary nebulae, and you are taking a trend of that. So the trend what is shown by that can be taken as that. If one is unexpected to change, and they have observed 5 planetary nebulae. Also, unfortunately, there are not more detailed study on that so far. And the OHP ratio is near solar values in the southern giant stream as well as the northern spore. Probably these two are connected by evolution actually. Northern spore as well as the southern galactic giant stream. And the outer disk of planetary also show the solar abundances, whereas the halo shows a very subsolar abundance. So this shows actually there is a kind of a complex interaction between this Andromeda and other galaxies, which has shaped this galaxy here with different large scale as well as small scale structures. And with this, for example, the emission line flux at helium-2 can be used to constrain the stellar temperature, whereas the high speed of flux can be used to approximately estimate the luminosity. So you can make them L star and T star can be easily understood. Again, this has uncertainties. This has to actually derive using models. But the problem is you cannot really go for accurate models for a bulk of planetary nebulae. It's not possible. So there is kind of a trade-off between these. And when they put it in the stellar evolutionary track, and they found that hydrogen burning CSPM models of facility loss and would fits well to this with and they derived the initial mass. And this shows that actually the distribution of the final mass as well as initial mass with the we have the different region, the galactic spool, solar, the halo, and the disk, and you can see that actually the mass is smaller at the red disk halo. So this is something which is unexpected. I know I said for in the previous case for the Magellanic Cloud, we saw larger stellar mass core mass for the low metallicity, but we don't see that. Maybe the number what they have taken total is not so many. What is happening here? We have to explain that. Okay, coming to this is that planetary nebulae luminosity function. This has been a very important this thing to understand it because this itself shows actually that our current understanding of the stellar evolution model is inaccurate. That's for sure. Because the thing is actually as per the current evolution model, the planetary nebulae semester luminosity should decline with time. So over the 10 gigayears of the time, it should have declined by at least 3 magnitude. But you don't see that. What is this actually? At different magnitude, you see that the number and then plot it. All of them, the peak luminosity, all of them, they touch at the same point. Okay, the absolute luminosity of this O3 line is minus 4.58. That was a derived thing. This is a empirical relation derived, but we have no understanding of this, why it is happening. Okay, and these distances, for example, secrets can be used to up to say 5 megaparsec the distance as a distance indicator, and you can compare this with the and they match within 10% of accuracy. So they work well. There is no doubt in that. But why it works well? Theoretical model don't support that. So where are we missing? That is something we should be understood, and we don't have many cases to study so far. So if you go on the extra-galactic regime, then there are many things to take, cases to study, and we have better understanding. We will have better understanding of everything. So that is why this is in. And there's some important findings of other findings from the other galaxies are given here. Just to briefly mention that there are studies on Fornax, Sagittarius, and different galaxies which are all below say 1 megaparsec of distance, which have been studied using the planetary chemistry. And PN abundant so much larger dispersion than the highest region. Probably they are wandering, they're near in a much kind of efficient way than the highest regions. And the third red job, they occur even at very low metallicity, after say over average of something like 7.8, below 7.8. But it is not the case for every observer. So the 3D is not actually dependent on only metallicity. There are some other factors. What are they? We have to see that actually. And in higher metallicity, galaxies are planetary nebulae are ionization bounded. Whereas in the low metallicity, for example, most of the planetary nebulae in the Magellanic Cloud are density bounded. Okay, so density bounded means actually radiation has escaped from the nebula. Ionization bounded means radiation is trapped within the nebula. And this is something that the gradient of the OH abundance is steeper than what is seen in the H2 region. This can be understood. These first 2 points can be understood because H2 regions they reflect the present metallicity thing and OH abundance, whereas the planetary reflects the older one. So it has become something more smoother. But what is not understood is actually at a particular distance, above the particular distance, overreach of PN is larger than what is observed in the H2 regions. That is something which is strange. And dust and molecules formation in the metallicity also, I noted it down just a few slides before. And in the bulge, galactic bulge, Spitzer has shown, so there are several metallic, there are silicate features which are crystalline in nature. Okay? Crystalline silicate features are there, but in the disk population we don't observe. However, there are many silicate features are observed in this disk population. They are not crystalline. They are much more in nature. And when we go to the Magellanic Cloud, there is no silicate features. Sorry, less number of silicate features. Okay, mostly it is dominated by the carbon features. Previous stuffs also we might have seen that. And fullerence, this is something very interesting. I noticed this in this paper. Fullerence occurrence is 5% in the Milky Way, 20 in the NMC, 44 in the SMC. So it is a very strong connection with the density. Okay, and again, this is 21 million feature is this are same, like hydrogenated amorphous galaxies. So this is the trend that they have given on the planetary dust and molecules and the low metallicity. And what is the issues in the current stellar models? Surely, the models which are worked out before 2016 is lacking in several factors. One is actually when I call star planetary into a flat star binary, making our planets or the last thermal pulse, no, that thermal pulse, that is open question. And observations shows galactic bulge BNE, they evolve 3 times faster than what is predicted by the stellar evolution model. And this is not explained why. Now, as I told you, the planetary luminosity function, it cannot be invariant as per the stellar evolution model. But there are something which has worked out recently. This is the Kesigi's paper in 2018. They have developed, they have used a new opacity function, and also the mass loss rate has more accurately been treated. And then the atomic, new atomic data was used, and they could explain to some extent that the luminosity of the central stars, okay, is almost same for a wider range of mass. So some explanation is there. Then this is worked out for a metallicity of 0.016. So how it behaves at a different metallicity, we don't know that. So they were unable to do that. So these two questions are to be addressed by any stellar model. They are very important questions which says actually that present stellar evolution models worked out by the people so far, they are not accurate enough. Okay, I'll just 2 slides and finish it with the MSc and the Extra-Galactic planetary what we can do. So we can use this MSc low resolution spectrograph with a resolution of 3000 this wavelength, and then with a multiplicity of say 3200, which is sufficient enough actually for planetary. It is an AMU of something more than 2 times, which is compared to the 8-meter class telescopes borrow. And this is a sensitivity limit of the telescope for a 1 hour exposure time. Is signal to noise ratio 2. So if you put all these numbers, for example, with a O3 width to 1.5 angstrom, signal to noise ratio of 3, then you get actually this is the number. And if this is the planetary luminosity, absolute luminosity, then this planetary can be detected by MSc up to 75 megaparsec. It's much larger than what it is. For example, this is the limiting magnitude for detection. I derived this, whereas it is 27.5 magnitude with the news at the K. Okay, at this news IFP. And if you go with the PMT, of course, it can be we can go up to 180 megaparsec. And the distance alone doesn't really give any much information because we need the chemistry and the distance to. Distance to the planet, that's a detection limit, sorry, that is the detection. If you want to determine the distance to the planetary nebulae, then you have to fit that planetary luminosity function. So you need to observe the planetary nebulae, which are at least 1 magnitude fainter than the brightest one. So if you fit it, cut these numbers, 1 magnitude fainter, then that comes to the up to 25 to 30 megaparsec. We can observe these planetary distances, galactic distances accurately to 10%. With TMT, you can go up to say 65 megaparsec. So we can, with this MSc, you can reach out to say visual cluster easily. And the chemistry analysis need to measure the O3 line at this wavelength, which is actually 50 to 100 times fainter than the O3 line at 5007. So except helium abundance, every abundance of what you derive require the diagnostic numbers for planetary nebulae, like what is the density, what is the temperature, etc. So to do that, we need to measure this number. So if you put 2 conditions, it's 1 magnitude as well as this to measure this number, then what you are getting is actually you can measure the abundances to the nebula up to 2.5 to 3.6 megaparsec. That means we can go away from the local group, we can even go to M81 group. And with TMT, of course, it is much. And this itself is a huge number because the local group contains more than 100 galaxies and M81, and so many galaxies are there, and their metallicities are down to say more than minus 2.3. Okay, average metallicity. So this will open up a new kind of area that our understanding of the planetary nebulae evolution at a very low metallicity region will become much more evident, and stellar models can be more accurately constructed. So these are my final conclusion, what we can really do with these new upcoming facilities. And I think That's not there. Thank you.
Actually, you have shown the spectrum of this planetary nebula. So, like, if I take example that sun-like star, it can become a white dwarf at the end, and then there's a planetary nebula around it. Like my low mass star, like less than 6 solar mass, they will have a planetary nebula and center mass of the white dwarf. This is the second, basically, branch where the clusters like Pete, where there is a very little young cluster, but there are a lot of white dwarf found in those clusters. They also become white dwarf in a smaller time, but they are massive star, like up to 7 or 8 times the mass of the sun. So they will might form a planetary nebula in some stage, and then what will be the difference in the spectrum of these two kind of stars?
There will be some difference in this spectrum because the latest stage, what I mentioned, this merger the mass transfer can become a very important role. For example, global clusters, you don't observe many planetary nebulae. There are only 7 or 8 planetary nebulae. I know that have been observed there, and all of them are expected to have formed from a mass transfer as a collision. Okay, so what happens is actually in those that elements which are produced during this at the third job and all that will have significantly altered with the thing. One is that thing, but the primordial but the other elements above oxygen and this thing, they will stay the same. So the spectrum will be, of course, it will be there, but the abundance pattern will become different. At low metallicity, carbon will be largely abundant in that.
One slide you showed actually so that the mean mass of that is 0.65 times mass of the sun, and that is basically the average mass of white dwarf as well. 0.6 point, that is the so.
That's
that is basically the average mass of the parent star, which has become the world.
No, the average mass of the assembly star.
That is the average mass of white dwarf is the same.
Yeah. Correct.
What fraction means reach?
0.5, I think this comes out. That's about 0.5.
Says that news itself will it detect MSC, so it will detect what redshift galaxies.
I have don't know what redshift MSC will get, but these objects which can be studied, for up to say 30 megaparsec, that transfer to say Z equal to 0.5.
One thing on the interpretation side, like MS, have people use fiber spectrograph for planetary nebulae because sky subtraction is an issue?
Yeah, it is there. Yeah, this that slide is by the news.
News is like
Yeah.
not a fiber.
Yeah, but it's I feel it. Yeah.
With a slicer.
Yeah, slicer. Yeah.
But fiber, the transmissions of 2 fibers. Taking 1 fiber per sky, 1
fiber for the object.
The transmissions are depends on stress of fibers. So you are trying to. I don't know. I'm just asking whether.
Yeah. For fibers, we need to have this source on the sky. Yeah, but what are the effects of that? We need to see that.
And again, what is the major difference between the planetary nebulae population and Milky Way and Andromeda?
Planetary nebulae?
The population of planetary. We know the global clusters are very different. Andromeda has a rich global population.
Yeah, they have rich. Yeah.
How is the planetary nebulae?
Well, actually, that Andromeda, not many planetary were studied well. What is the thing? There are many detected. That only the detailed study what I have seen is this one. What are their how their population?
In terms of numbers.
We expect more. For example, the theoretical expectation of number of planetary in Milky Way is 20,000. It is more in Milky Way Andromeda. Metallicity. It also has no true metallicity form. Andromeda. Yeah. So that could be because of the some merger in the So basically need an IFP system with to detect any planetary and understand that. As I know that this is the latest to say, they have studied but they have studied, well distributed in arrow population and the spore and the stream and so there are some interesting, but it's better, even it will be always good to have kind of more number of planetary there, and that will be very helpful to have a two-dimensional materialistic map.
He says that there will be hundreds of galaxies, around 100 galaxies in the local group, where you can measure the planetary luminosity function. But most of these galaxies are low mass dwarfs. So the question is, do you have a planetary luminosity function for any dwarf galaxy? I expect.
Yes, that is what I said actually. Dwarf galaxies also, the maximum luminosity of the planetary array is absolute luminosity is same. That is what the observed one. These dwarf galaxies also they observed, and they have estimated the distance using the planetary luminosity function as well as from the sequence, and they match quite well. So you are correct actually at the low metallicity in the dwarf galaxies, and the evolution should be different, and we don't expect the luminosity to be that high, but they are there. It is there. It is observed. So that is the thing that I said, it is something important to be addressed using the excited studies. Yeah.
Long live India and France friendship.